let me introduce myself. My name is Adam Zalewski. I've been a Zoom master for a few months before that as part of the series, but now I have a second hat as the SPE chair, and I'm really privileged to be in this position to represent you as members and make sure that all our activities are adding value to you in your professional lives. Second of all, the second privilege I have today is that we have a quite important announcement. So last weekend, there was a regional section officer meeting in Budapest, as well as an award ceremony. So we had a number of people that have received an award during that event, but one of them has not been able to attend. So I would like to just use this brief moment to award his award before I pack it up and send it by Royal Mail. So I'm really excited to present a Regional Drilling Engineering Award for the North Sea region to Junichi Sugiura from Sunvin Technologies. He has an extensive engineering career with over 150 patents, filed 70 publications. He's a chartered petroleum engineer, chartered energy engineer. He's involved with both Society of Petroleum Engineers and being a fellow of Institution of Engineering and Institution of with the Energy Institute, and he has supported SPE through many years, especially through his involvement with ATCE and the EADC and SP Drilling Conference. So I would like to present this award that I have neatly packed in here to Junichi Sugiura. So Junichi, this is for you.
All right, thank you very much.
In the post at some point. And yeah, thank you very much for everything that you have done for SPE and the drilling profession for many years.
Thank you very much, for SPE and of course, London section. And lately, I'm attending all the meetings, organized by Adam team, all you guys, the committee members who organize these, educational programs and the presentations. I enjoy it so much, and thank you very much for organizing all this and giving us opportunity to disseminate the knowledge. And I will continue to attend your webinars, and one of these days, hopefully face-to-face meeting and having a great conversation.
Fantastic.
So, thank you very much.
Thank you very much, Junichi. And with that, that's my moments in spotlight. I will hand over to Tim so he can introduce our first speaker. Thank you.
Thank you. And it just occurred to me, Adam and Junichi, what about a non-fungible token rather than the actual physical object? Okay.
But you can buy and sell them, so that might be too expensive within a few years.
Okay. Dr. Fatai Anifowose, thank you very much for attending and offering to give a talk to us. And you are a specialist at Saudi Aramco in computational intelligence, machine learning, and data mining. And I know everybody has read your CV in order to attend in the first place. But the title of your talk, The Contributions of Computational Intelligence to Petroleum Reservoir Characterization. Fatai, the floor is yours.
Good evening, everyone. I hope I'm loud and clear. Thank you. It's a great pleasure to meet you virtually, my colleagues in SPE London, SPE Europe section, right? Okay, thank you. So it's a great pleasure, and as introduced, I will be sharing with you the contributions of computational intelligence to petroleum reservoir characterization. So my name is Fatai, as introduced by Tim, and yeah, I don't have to waste more time. Let me just go straight to the presentation. So in the presentation, I will start with an introduction to the concept or the process of reservoir characterization. I know you guys are experts, but in order to do the required justice to the topic, I think I need to start from there. Then I will discuss some of the traditional approaches to reservoir characterization. And of course, before I link that to the contributions of AI and machine learning, I will give a brief introduction to machine learning, and then I will share some of the contributions. And of course, I will conclude with a few takeaways. So what is reservoir characterization? Just something to start with. It's the process of estimating reservoir properties. I think this is my favorite definition. It's very short and cute. So when we estimate reservoir properties, then we want to know the impact they make on reservoir performance. And of course, we use these reservoir properties to build reliable reservoir models. And these models are used to simulate the behavior of reservoir fluids under different circumstances and to find the optimal techniques for maximum production. Reservoir characterization is an integral part of formation damage assessment and mitigation. So we study how the various reservoir properties influence the magnitude of formation damage. Furthermore, it provides critical information on the distribution of reservoir heterogeneity and, of course, petrophysical properties. Some of these reservoir properties are the positional environment, lithology, porosity, fluid saturation, grain size, rock strength, and permeability. Of course, there are more than this, but these are just the key examples. These reservoir properties are correlated with reservoir qualities, quality indices. That is, they are indicators of reservoir quality. And the process of reservoir characterization is multidisciplinary. It combines information from various fields. We talk of petrophysics, from geology, from petroleum engineering, geomechanics, and of course, geophysics. Reservoir properties are obtained from the analysis of different sources of data. We talk about core data, well logging, seismic, mud logging, production, geomechanical data, pyrolysis data, and geochemical data. And the major goals of reservoir characterization are to determine the presence of hydrocarbons. And when we do that, we want to determine the optimal techniques to use to extract them, and of course, to find ways to increase production. So how do we get data for reservoir characterization? Data are gathered from various sources, from the field, surface and borehole, and the lab. Now let's take them one by one. From the field, we talk about LiDAR or laser, seismic, and outcrop. For LiDAR, it can be from surface to here, from air to down to the surface. For seismic, it could be onshore, offshore, and of course, for outcrop, then we have to go to the field, sometimes to some remote areas to collect some outcrop data. For the surface or the borehole, we talk about microseismic, mud logging, and of course, wireline logging. For microseismic, from the borehole, we shoot and we receive at the surface. For mud logging, we capture the gases that are liberated as the drill bit, grind through the rocks. The gases that are liberated are measured through gas chromatographs and gas spectrometers, and they are measured, so they are quantified. So we want to see what is the correlation between these gases and various reservoir properties. And of course, wireline logging, we capture the interactions between various physical properties like electricity, like nuclear materials, like sound, and how they interact with the formation rocks and with the fluid. And then we capture all these at the surface. And for the lab, we have rock samples and fluid samples that are brought from the field to the lab for measurement. So for rock samples, we talk about core samples, and from the core samples, we can extract some plugs. From the plugs, we can do some thin sections. So, and from each of these samples, we measure varieties of reservoir properties. For example, from core samples, we want to know the lithology, we want to know the grain size, we want to know the positional environment. Okay. From plugs, we want to perform some measurements like mercury injection to measure saturation, permeability, and so on. From thin sections, we want to have some idea about the grains, morphology, the pore, the shape, the pore throat, and so on. And from fluids, of course, we want to know the fluid types, from PVT measurements, and so on. So all these are different kinds of data that are pooled together to do reservoir characterization. Now, each of these data sources have their own challenges. For example, the seismic or the LiDAR, they have issues with noise. They are usually noisy. So you have to do a lot, you have to exert a lot of effort to denoise the data and then to begin to analyze and interpret. Sometimes they require complex workflows. Seismic data is known for its low vertical resolution, and sometimes it's costly to acquire in terms of personnel, equipment, and logistics. For the outcrops, it involves traveling to some remote locations, sometimes in the forest, sometimes in the desert, as we have it in the Middle East. And sometimes there are traffic concerns, there are safety concerns, and so on. And for lab measurements, we have issues with this data being very few, because only few samples can be taken. You cannot take samples from a whole reservoir section or a whole formation. And then sometimes there are human errors in handling these samples or even in recording the measurements. And also, it's a time-consuming process. Also, there are issues with mud logging and wireline logging. Sometimes you run into problems with bad hole sections. Sometimes there are gas kicks that are incorrectly recorded in the mud logs, and so on. So there are challenges. And these challenges are actually giving us the opportunity to apply artificial intelligence. And when do we do this? Actually, I like to start with this. We don't have to apply artificial intelligence in all cases, because some people have erroneously taken it as a magic wand nowadays, that it must work, it must solve all problems. No, you use artificial intelligence only where it is needed and only when it is necessary. So some of the instances when we can take opportunity of AI to address our challenges, the first one is when there is a process that is repetitive and it has very clear procedures. So this is an opportunity to use robots to handle this repetitive task, and then we free some humans to focus on more important tasks. When safety is a concern, then we can use robots. We can use some intelligent algorithms to handle the situation. When there is no predetermined relationship, when there is no standardized equation. For example, one of my recent research areas is to explore how to link mud gas data to various reservoir properties. Okay. For example, up till now, there is no established equation to relate the mud gases, the methane, the ethane, the propane, the butane with, for example, porosity or permeability. There is no equation. So this is an opportunity to apply artificial intelligence. And also, when such relationships or equations do exist, but they are too complex to handle or to explain. And sometimes we want to keep them simple, so we tend to oversimplify such equations. And in the process of doing that, we bring in a lot of assumptions, some of which may not be realistic. So in such situations, I say, well, why not try to use artificial intelligence in that situation? And also, when there are rules, but the rules are constantly changing. For example, when different rules apply for carbonate and clastic, different rules apply for dolomite and whatever, and it's becoming cumbersome to use to apply some of the traditional approaches. Then you can bring in artificial intelligence to handle the challenge. Also, just a slide away, I mentioned that one of the limitations of laboratory data is that they are very few, they are limited. So if you want to generate a log from out of this point data, then you think of applying artificial intelligence. Also, even when there are established workflows, but we just want to experiment an alternative. So I see AI, machine learning as alternative methods that can just be explored. If they work better, that's fine. If they don't work better, then we stick to the traditional approaches and we keep things going. And of course, when we have large amount of data such that it becomes challenging to handle this amount of data with the traditional approaches, then we think about applying artificial intelligence. Now, I have used the words artificial intelligence in the context of the topic, okay? However, I would like to go in the line of the computational aspect of AI, which is what the topic actually is pointing to, which is computational intelligence. And under this, I will be focusing down to what is called machine learning. So how do these terms relate to each other? So why and how do I move from artificial intelligence down to machine learning? So we'll be seeing that in a moment. First, what is AI? Again, I like this very short and cute definition. There are so many of them out there. It is the science and engineering of making intelligent systems. So these intelligent systems can be in form of hardware, in form of software, or in form of both of them combined in one. When we talk about hardware intelligent systems, we talk about something like robots, okay, that are used, for example, to handle some core samples. When we talk about software, we're talking about some intelligent softwares that follow some rules or to learn from data and make some predictions. And then sometimes we have some intelligent rovers that combine the mechanical parts of a robot with some intelligent software running in them that assist the mechanical parts to take some actions based on certain conditions. So this slide is very important. A while ago, I mentioned that I will be transitioning from the use of AI, then to CI, to ML. And also some people, confuse all these terms along with neural networks. I could remember I was at a conference some years back, and after my presentation, someone came to me and asked, what method did you apply in your work? Is it AI or neural networks? I was like a little bit confused with the question, but I had to, give a very short lecture before I answer the question. However, I like to use this, what I call the AI family tree, to explain the relationship among all these terminologies and try to explain their differences. Now, we start from AI, and I just defined AI a slide back, that it is the science and engineering of building or creating intelligent systems. So this is the root of everything. So AI is the beginning. And when we say AI or we mention AI, then we are actually referring to a wide range of other technologies, such as NLP, the natural language processing. We talk about expert systems, we talk about robotics, and we might refer to computational intelligence. We all know natural language processes are systems that are used to do language interpretations, do some voice recognitions, and so on. Expert systems are rule-based systems, okay? You program in some rules that will lead you from some input to certain decisions, okay? Robots are robots. We all know that. This is very clear. Computational intelligence is simply the computational aspect of artificial intelligence. This is where you deal with numbers. This is where you deal with data. You mine data. You try to extract knowledge from data. You try to discover patterns that are hidden in data. This is the CI, the computational aspect of AI. And when we do all this, we try to discover knowledge, recognize patterns, and we mine data. We are talking about machine learning here. So this is how they relate to each other. And there are many methods that can be applied to perform machine learning. So this is when we talk about neural networks, random forest, support vector machines, decision tree, fuzzy logic, and so on. So now from the tree, we can see how these four terminologies, how they relate to each other and how they differ also from each other. So I will keep it at that. I hope it's clear. So from now on, I think I will be switching to machine learning, which is actually very close to what we'll be doing. But at some other time, based on the context, I will transit back to AI as will be required. Now, very quickly, when we say we are doing knowledge discovery, pattern recognition, data mining, this is the process. This is the process. So as I said, everything starts from data. So we start from data. So the first step is to select from a huge data repository. We select the kind of data that we want. Do we want to combine, wireline logs with mod logs, or we want to combine thin section data with core data or with plugs and so on? So we have to select which of the data will provide the new knowledge that I'm trying to mine or to discover, okay? So after selecting the data, then we have to pre-process, because the raw data usually has noise. Sometimes we have missing values. Sometimes we have unrealistic values. So we have to apply some methods to clean them. Okay, sometimes after cleaning, we might want to do some transformations, okay? We may want to do some log transform, some Fourier transform, whatever, and so on, as may be required based on the problem that we are trying to address. After that, from the transform data, then we want to mine the knowledge that we want based on our objective. So we want to discover some patterns that are hidden in this data. Then we apply different methods. One of them could be machine learning. It could be pure statistics. It might be just visualization, and so on. So whatever method we want to use, we use it based on our objective, and then boom, we have the knowledge that we are looking for. Then we evaluate this knowledge. Does it address the challenge that we are trying to address? If yes, then we say, okay, now we found something. If no, then we go back to the first step, and then we reselect the more relevant types of data that will lead us to the desirable conclusion. And this whole process translates to different technologies, different methodologies that can be used to do the pattern recognition or the data mining. As I said, it can be just pure visualization, okay? It can be just pulling out some records or some data from a database and then do some wrangling, and then we get some new knowledge. It might be machine learning purely, and it might be other forms of technologies. very quickly, now let's leave AI a little bit and focus on focus deeper on machine learning. What is machine learning? It is a process of teaching computers to do what humans naturally do. And what do? We learn from experience. But the way we let computers learn from experience is to provide them with historical data. So we gather all the data, the wells that we have drilled in the past, we bring together all the data, and we try to see what we can learn from that history. And also, we let these computers and algorithms learn from this data by extracting some hidden patterns and knowledge. And then these algorithms also can adaptively improve themselves as we had more data. So more data leads to more experience, as humans do. And also we find these patterns in data to make better decisions and predictions. So this screenshot is from MATLAB. I love it so much. It makes things very simple. So when we talk about machine learning, then it's either we are doing unsupervised learning or supervised learning. This might be a little bit too simplistic, but I try to bring everyone along. And one example of unsupervised learning is the popular clustering. So here you have a group of data, you have no idea what the output will be, and you apply some algorithms to help you to identify some natural groupings in the data, some natural clusters, okay, that will tell us certain stories. So, and when we do supervised, then we talk about whether we are doing classification or doing regression. Here, we have both the input and the output. We have both the questions and the answers. So we present these two to the models, to the algorithms, to the computers, for them to learn. So the computer know when my wireline logs are this, then my porosity is this. When my mud gas is this, then my hydrocarbon fraction is this. So we give both the question and the answer to the algorithms to learn from. And when they become learned, we call them models. And when do we do classification? When the output or the target or the answer is in form of labels, or when it is qualitative, okay? Is it yes or no? Is it good or bad? Is it lithology? Sorry, in terms of lithology, is it carbonate? Is it plastic? Is it dolomite? Okay, so when we are dealing with this kind of qualitative descriptions, then we do classification. So in that case, we assign labels to these properties in order to learn the algorithms with them. And when our target, when our output or the answer is a continuous variable, then we say we do regression. And these are the various methods that we can use to perform each one of them. So the popular k-means, the fuzzy c-means, and the SOM, all of these are used for clustering. Then most of these methods can be applied to both classification and regression. This slide is also very important. It gives us the generalized workflow for supervised machine learning, because this is, we do more of supervised than unsupervised. So everything starts from the human, from the user. And this is one of the reasons why humans cannot be removed from the workflow. Human will continue to be central to the smooth running of all these machine learning processes. So the human ingest some data, okay, do some cleaning. This is very similar to the data mining and pattern recognition workflow. But here, it is more focused on learning from data through the process of supervised machine learning. So from the data, we do some cleaning, we can do some transformation, and then we have a split here. We keep part of the data to validate the model after training. So we try to train the model, which could be any of neural networks, any of support vector machines, random forests, decision tree. We use this training data to build this model, and then we continuously test the performance of this model, okay, by using both the training data and the testing data to check for, are we overfitting, are we underfitting, and so on. And based on the result of that, then we have to go through a number of loops until we arrive at an acceptable level of performance. After that, we say that, okay, we are ready to deploy this model into production. And even during production, we keep monitoring this model to know when the performance deteriorates. And after that, the loop goes back to the human to retrain the model by maybe removing some data or adding some new data, and then the whole process continues. So when we are doing machine learning, especially supervised machine learning, what is our goal? Our goal is actually to avoid the two extremes of underfitting, where we have low variance and high bias, and overfitting, where we have high variance and low bias. So where we want is actually a point in between these two that give us the optimal performance without, tilting to any of these two extremes. And if we look at this, graph, it explains the optimal point where we try to optimize the model to avoid these two extremes. And I will, spend a few seconds to get this across. Now, when you start to optimize your model, okay, you start from a simple model, then you keep increasing the degree of complexity gradually. And how do we increase the complexity? I will give an example of neural networks, okay? One of the controlling parameters is the number of layers, and for each layer, the number of hidden neurons. So the more you increase the number of hidden neurons, then you are increasing the degree of complexity of this model. So when you do that, initially, your errors will be high. Sorry, I didn't label that very well. The y-axis is the error. So initially, the error might be high, okay? That is when your model is still gathering some power, so it is underfitting. So gradually, as you increase the complexity to match the complexity of the data, then your errors begin to decline. So your model is improving. It's improving. It gets to a point, which is this dashed line, when your training error continues to decrease. However, your testing error now begins to increase. This is the point when overfitting, creeps in to your modeling process. So this is when you have to take some, steps backwards to say, no, I'm not going in that direction. Then this is my optimal point. And this is when you have a trained model that you can deploy into production. So this slide is also very important. Now, very quickly, before I go to the contributions of machine learning or AI in general, I would like to quickly go into the latest advances that we are talking about in machine learning. Nowadays, we talk about hybrid learning. Okay, hybrid learning is basically when we combine two or more existing or traditional algorithms. okay? Such that we try to use the strength of one to overcome the weakness. So we have two or more independent algorithms, but fused in a way that they cooperate with each other and they work as a single entity to solve a problem. And a very good example in the field of machine learning is the ANFIS, the Adaptive Neural Fuzzy Inference System, which is actually a hybrid of fuzzy logic, which is a standalone machine learning algorithm, and neural networks, which is also a standalone algorithm. So the two of them work together cooperatively to form a single algorithm, which is called ANFIS. And very quickly, ensemble learning is basically combining different opinions, okay? It's like having a committee of models, okay? Working individually to solve the same problem. They work individually to solve the same problem, and their outputs are combined in a very nice way, in a very smart way, I would say, to evolve a single ensemble decision, okay? And a very good example of this is the random forest, which is actually a combination of several decision trees. And the last one is deep learning, which is basically the traditional algorithms that are optimized with a very high degree of complexity to be able to solve a very complex problem through a very complex data. And a very good example is the neural networks. So we have the traditional neural networks, which contains 1 or 2 layers, maximum 2 layers. And now this is being called shallow neural network. So compare that with deep neural networks, which contains several layers, even sometimes running into hundreds or thousands in the case of a convolutional neural network. So this is a typical example of this, and each one of them has specific instances where you need them, as I have mentioned. So in the order in which I have discussed them, we also have increased order of accuracy. So putting everything together in this single chart, we can see that AI, as we saw in the family tree, AI was the root there. Here, AI is the superset, so to say. So inside AI, we have machine learning, which is ML. And inside machine learning, one of the latest advances is deep learning. So this is how they relate to each other. And I hope this is very useful. Now, very quickly, how do we now link the AI and the machine learning and the various advances to what we now call big data? So if we continue to add more and more data, then how does the traditional approaches, or what we now call the shallow models, how do they compare with deep models? Basically, the shallow models are limited in a way that as you continue to add more data, it gets to a point whereby the accuracies are no more significant. They plateau at a point. So you don't get corresponding accuracy based on the amount of data that you are adding. However, for deep learning, research has shown that the more the data you give to the model, the higher the accuracy goes. So now, enough of those backgrounds and overviews. Now, what are the contributions of AI? Now I have switched back to AI in the broad sense of, bringing in NLP, expert systems, robotics, and of course, computational intelligence. Now I have gone outside of machine learning to a wider perspective. Now, let's start from seismic. Okay, a lot of research is ongoing nowadays on how drones, which are a form of robots, drones can be used in seismic data acquisition, either in dropping the geophones without having to navigate through the forests, or to climb the mountains, or to drive through the valleys. Now, this is being studied. Also, we have smart algorithms that are being used to analyze and process seismic data. And also, a lot of smart algorithms are being used to interpret seismic data, to pick the first arrivals, to pick the traces, to identify the salt domes, to detect fractures and to detect bedding planes, and so on. AI is actually playing a very big role nowadays in seismic data acquisition, processing, and interpretation. In outcrop, okay, AI is also playing a major role. Instead of allowing geologists to go through a lot of traffic concerns, safety concerns, to go to some remote areas to physically examine outcrops, now outcrops are being digitized. You use drones to take high resolution photos and videos, then apply some photogrammetric technologies to digitize these photos and videos, and then boom, on your desktop, you have a digital outcrop that you can interact with. You can rotate, you can zoom in, you can zoom out, you can do measurements right on your desktop rather than going to the field. Now, core samples, the core description process is being digitized. At this level, I mean, we all know is a popular saying that the core description process is human-centric. It relies heavily on human intuition, and it is highly sensitive to human errors as well. It's been said that if you give the same core samples to, let's say, 3 geologists, or more precisely, sedimentologists, most likely they will give you different results. And even worse than that, give a single sedimentologist some core samples and ask him to describe them at different times of the day. The morning, the afternoon, at night. Most likely, this same individual will give you different results for the same core samples. So this has actually given the machine learning community the opportunity to bring in robots and also machine learning to actually automate this process and make it more consistent, to remove the human subjectivity in the process. So this will definitely increase the accuracy of the subsequent processes. So machine learning has been applied on core images, core samples, in order to identify beddings, laminations, lithologies, grain size in some cases, and most importantly, the positional environments are now being captured automatically by using machine learning. In the same way, thin section analysis has been automated, okay? Just like the core samples, again, we get different results from the same thin section from different geologists, okay? But in order to increase the consistency and the accuracy, the photos are being digitized, and then machine learning algorithms are applied on them, coupled with advanced image processing to get very accurate, consistent results from thin sections. I could remember working with some geologists. The same thin section, I got different porosity estimates from the same thin section, but from different geologists. So that actually gives the opportunity to bring in machine learning and other technologies in order to make this process very consistent. Now, moving to logs, I worked on this project to generate a continuous log of reservoir or rock cementation factor. Okay, as I mentioned a while ago, cementation factor is one of the data that are acquired from rock samples, so they are limited. In a whole reservoir of about maybe 70 feet, you may not have more than 2, 3, or 4 measurements of this. So in most cases, engineers, they take the average of this and then they plug it in as a constant in their saturation equations. This is not very accurate. Okay, it will be more accurate if we generate a log out of this. So instead of working with some constant values, we can actually work with logs, and that will bring in the expected or the apparent heterogeneity that occurs in the formations in the reservoirs based on different lithologies. So in this particular work or this plot, the red dots are the core points that we have that we acquired from the lab, and then the blue line are the logs that are generated out of it. So this is just a part of the plot, just to show this idea. Also, with wireline logs, sometimes we have missing logs due to different reasons. Sometimes due to tool failure, some logs are missing in certain sections. Sometimes due to bad holes or due to a problem with the integrity of the borehole. Sometimes a whole log is missing sometimes. So we can actually use machine learning to regenerate or to fill up the missing sections, or to even generate a whole missing log. This has been done. This is one of my work as well, but has not been published. Also, this is one of the results I got from predicting porosity. Try to predict hydrocarbon volume fraction from mud gas data. Traditionally, this is being done from wireline logs, but in an attempt to make this property available ahead of wireline logging, even if possible in real time while drilling, this can be done. So my proponent actually told me that with R square of 0.82, this is a very good result. I mean, if I can have an idea of my hydrocarbon volume with this level of accuracy before I do logging, wireline logging, then this is good for me to move on in my analysis. These are the words of my proponent. So these are the few examples of how AI, machine learning, robotics, drones have contributed to the progress of reservoir characterization and the oil and gas operations in general. So to conclude, we have seen that the reservoir characterization process is complex because it involves bringing together different chains of data from different sources, and it is also multidisciplinary because you bring together domain experts from geology, geophysics, petrophysics, geomechanics, and so on. And this process has contributed a lot to the industry, to the reservoir modeling process by reducing the extensive, AI has contributed immensely to this field by reducing extensive human intervention in the case of core description automation and thin section analysis automation, and also in seismic data acquisition. also, it has brought in, improved consistency and accuracy as well. It has, led to significant reduction in cost and time. However, there are still challenges. I'm not saying AI has come to, make the whole thing, very easy. No, there are still challenges. Maybe I will mention a few of them during the Q&A section. So I think I've spent some time, and I think this is the right time to stop, and then I'll be glad to entertain any question from the audience.
Wow.
Thank you very much.
Thank you, Fatai. I have to say, I mean, your slides are exceptional. Really, the way they unroll and then illustrate the issues. So yeah, very good. The picture takes 1,000 words, and you do show that very well.
Thank you so much.
Yeah, no, really amazing. Yeah, and I'm sure Kate will want a copy of them if you can release anything or sanitize it from your company, and then let us have something, because we'll then put it on our website, so those who aren't here today can at least go through them.
Yes, sure. It's already approved, and then I can easily release it. Yeah.
Okay. Well, first of all, since there are so few of us, can I please ask you all to come off your microphones? The reason is that we're going to have a conversation rather than me doing something like saying, okay, Jacob, you asked a question. We are sufficiently small numbers that with a little bit of discipline, we can simply have a discussion with Fatai and indeed with each other as to, and let's do it. So Jacob, come off your phone. You're mute, please. John, please. Oluwalua, please. Peter. Please just come off so that it's easier for Fatai to see you and hear you, and then we can have a proper discussion. If you're that, okay, well, it doesn't look like I can get people to come off their mutes for some reason. You do understand what I'm saying, please? Please come off your mutes. Unmute your microphones so we can chat to you. Yeah, that's right, yeah. Okay, oh well. Okay, so I mean, I'll throw it open. I've got my own questions, but so Adrian or anyone, do you want to ask a question? Yeah, okay, Adrian, go ahead, ask your question, and then let's hope others will pitch in.
That was a great talk. Thanks very much. So you're basically trying to extract knowledge, particularly from this computational intelligence stuff. So sort of how do you know when you've actually determined the truth? Because sort of what criteria do you apply? So in the example you said you picked the 3 polynomial, but you don't know what the polynomial is in other cases. So how do you? So that's the question. So how do you know what the uncertainty and the truth you're creating? Because you're sort of creating data. You're just creating new data, aren't you? So I'd love to know what the answer is.
Thank you very much. Let me start by saying this. The uncertainty in our data is actually one of the challenges that we are facing with machine learning. So there is no single data that has no uncertainty. So we can only try to reduce it as much as we can. And that is why one of the key processes in machine learning modeling is data quality assessment. So in order to avoid garbage in, garbage out, we have to invest heavily in data QC. And this cannot be left with the machine to do, okay? And if we do that, the human will even take the lead. So determining the accurate data that goes into machine learning modeling comes from the human first and foremost. And then the human can design some systems that will, that will help to improve the quality in order to reduce the uncertainty, and then we can go on with machine learning. So at a point, as I said, there is no 100% accurate data, so we have to live with that uncertainty. However, the goal is to keep it to the barest minimum. I hope I answered that.
That's right. So then the follow-up question is from the last question is, so obviously that you've got missing data and you're trying to infill it with basically numerically. I mean, the best way we've historically done it the last 40 years is go out and get proper data or new data. So your petrophysical example, you only had 2 or 3 points which showed the saturation exponents. Well, that just basically means if that's an issue, we just take more core and we take more samples. And then, but you're now trying to use computational to sort of fill in the science which should have been measured in the first place. So I just wonder how you see the value of new data versus what you're trying to do.
Yes, you are right. It's like creating new values. You are right. But based on what? Based on history. Based on history. We cannot afford to go back to the field and get more core samples. We cannot afford to do that. We cannot afford to go back to the field and get new fluid samples and then go through new cycles of experimentation and laboratory measurements. So that's where the machine learning comes in. Okay. However, based on what? Based on the pattern that we already have in historical data. We have a lot of core samples that we have measured. We have a lot of thin sections that we have analyzed. We have a lot of all these samples. So we simply gather all of them together and then learn from the patterns in them and then use that pattern to generate those missing values. So it's not like a blind process. It's actually based on science, based on the patterns that are actually based on the physics from the tools, from the lab, from all that we have. I hope that makes some sense.
It makes sense, yeah, thanks.
Thank you.
It's interesting picking up on Adrian's point. I mean, well, 2 things. One is that are you saying that when you run these models, you constrain them to the physics so that they don't produce unrealistic or not physics possible outcomes? Is that part of what you do?
Yes, because all the measurements that we use, okay, sorry, just 1 minute. Sorry. My laptop is running out of battery. Sorry about that. So now, yeah, okay, I'm back now. So yes, you are right. The physics comes in from the data that we use, okay? When we say we use wireline logs, what are we doing? We are using the physics, the measurements that come from the physical interaction from the wellbore. When we use mud gas, it is the physical measurement of the gases that we get. Core samples, the same thing. So,
yeah, but when you're forecasting from those measurements, I mean, as you rightly say, the models will always have a degree of error in them, and I'm wondering whether you try and constrain the forecasts or the predictions so that they remain within physics boundaries, and you do that explicitly so that you can't have more volume than there was to start with, or whatever it might be you're measuring, or is there something like that you do?
Yes, it includes that, and actually that's what goes into the optimization process. So when we do machine learning, I mean, when we do training, we are trying to say, okay, this is our target. This is what we want. So how do we bring the model to be as close as possible? So we have a target, and that target again is based on certain physics. So we are trying to, constrain ourselves to the limit of the physical interaction or physical relationship in the data.
Okay. Well, I can, before I ask any more questions, does someone else want to pitch in with a question?
I think there's one question in the chat from Jess.
Okay. What's that say then?
Jess, would you like to ask your question, or?
Go ahead. Yeah.
Hello. Good evening.
Hi. Good evening.
Yes. This is Jesse from Nairobi, Kenya.
Oh, nice to meet you.
Nice to meet you too. My question was on the physics-guided machine learning. I was asking if we expect maybe in the near future we should have more confidence in using them as compared to the conventional physics-based models. Yeah. So I just wanted maybe an opinion from you if we expect to get more confident with these models.
Thank you, Jesse, for the question. Honestly, this question comes almost in every presentation I make, and I know why it is very important. Now, let me start by saying that the conventional physics-based models are very good. Okay. However, the limitations they have is that sometimes they are very complex because we want to bring in every single interaction, physical interaction, chemical, whatever, want to bring that in. So in the process of doing that, they become very complex. And in order to simplify them, sometimes they become oversimplified. So we are bringing in too many assumptions in order to simplify the models. So instead of, and those simplification processes actually introduce more uncertainties. So what do? Why not just learn those physics directly from data? So this is what machine learning is all about. All the physics are hidden in the data. So let's bring them out. Let's use them to teach the machines. Then let's make predictions based on them. So we are still working with the physics of the problem, only that we are looking at the patterns in those data, the patterns in the physics of those data. Nowadays, some people are claiming that they are trying to combine physics-based models with machine learning. I think, in my opinion, that there is no need for that. The physics is already embedded in the data that we use. We don't engineer our own data. We use physical data. So the physics are already in the data.
Well, I've got a couple more general questions. So, I mean, you work for Saudi Aramco, and it's quite clear that as a company, you're pretty advanced on these things. What have been the signal successes, the really important successes that data science has achieved within Saudi Aramco?
Thank you very much for that. The company is really investing a lot in data science, in digital transformation. And the backbone of that is, of course, AI, along with other technologies like IoT and so on. So the company is investing in, putting more sensors in the field to acquire real-time data, and then handling those data with machine learning models in order to get real-time interpretation. And not only that, even machine learning models are being used to process even historical data. So back and forth, the company is really investing. Every department has a digital transformation group that interface with each other at some levels, and the company itself has the upstream business line now has a digital transformation officer that oversees all digital transformation activities that goes on in all the departments. So yeah, the company is really investing in these technologies, and we are seeing results. As I said, there are challenges everywhere, but we are working to overcome those challenges.
Are you not able to divulge some brilliant example because it's secret, something that you've done, like reduce the modeling time for a big reservoir by a factor of 100 or something? Is there anything you want to actually say, look, this is the one we're really proud of, so we can just get a feel for what one of the most advanced companies is doing?
Okay, I can mention a few of them that are already available in the public domain.
Yeah.
Actually, many things are going on in Aramco. There are certain, there is a undersea robot that was developed by the geophysics technology department in the Advanced Research Center. And it has been tested, and it has been used as a receiver. So it lays on the seabed. So some signals are sent from the surface, and then it does some recording, then it is retrieved later, and the data is analyzed to measure certain things. There is what we call petrophone. This is the process of the sound of the drilling bit is captured at the surface, and this is processed by some using some machine learning algorithms to detect lithology in real time. So as you know, different rocks give different sounds. So these different sounds are correlated with certain lithologies, even with porosity, with different reservoir properties. So from the sound of the drilling bit, we are able to predict some reservoir properties, and it's really working. And even this tool has been commercialized. So this is one of the achievements. Also, I can continue on and on. There is honestly, there are many things that we do. So if you want more, I can go on.
I have to say that I was just talking to a British oil company this morning about the need for very detailed cuttings analysis in this particular case. So that, and of course, you're saying, well, you don't need to wait for the cuttings. You know what they are just by listening to the damn things. That's pretty amazing, actually. Are there any other questions or comments people want to pitch in on? I don't want to hog the whole time. So one who wants to pitch in?
Yeah, I would have a question, Fatai. So
yes, please.
One of the things that I've seen when using machine learning is, for example, when you're doing natural language processing, you can have already a pre-learned model that will kind of understand how the sentence is structured, right? So you don't start from scratch. Similarly, for image understanding, you don't start, we start with some kind of, boxing algorithms, etc. When you set up something in reserve engineering domain, do you start with just bare bone, algorithm, or do you have some kind of packages that would understand a little bit already before you feed a particular field in? Or is it always straight from scratch based on data that is available?
I would say that it depends on the circumstance.
Okay.
In one of my projects, okay, my proponents will give me some very clean data, well-curated data. So I just apply them directly on my machine learning algorithms. Yep. However, there are some other projects in which the user is not ready to do that. And even I prefer that they don't do that because, part of the goal is to automate some of the time-consuming processes. So I start from scratch by writing some codes that connect directly to the database, pull out the data, then do some cleaning based on certain criteria that the user indicates. Okay. In this typical study, do you allow your input data to have negatives? Does it make sense?
Okay. Yeah.
If yes,
so you have just some
if
automated pre-cleaning of the data.
Automated QC, and then and also even the machine learning models, in order to actually, this is one of my projects which I call AI Lab. Okay, we find that because the everybody wants to try to see what machine learning can impact in their work. So people continue to have interest in machine learning, but not everyone can learn coding, at over 50. So I built a tool.
I think below 50, not everybody can code either. So that's
yes, I agree with you. But not everybody is ready to do that, I guess. So I built a tool for them without any idea of coding, without any idea of machine learning. Very intuitive tool, user-friendly. They can actually move directly from raw data to predictions. And from there, they can put the predictions into some subsequent applications, like end-to-end solution. So it depends on the scope, on the objective of the study. It depends on many factors. Yeah.
But do you think there would be a scope, for example, for pre-trained, feed thousands of sandstone reservoirs or sandstone of limestone reservoirs? And, when we have very small amount of data, right, you could do much more if you have already this pre-trained model that's on those interactions.
Yes.
Okay.
Yes, we do that. We do that. I mean, not in all cases that you have to start afresh. I mean, from the scratch. We leverage, those opportunities, I would call them. Yeah.
Brilliant. Okay.
We do, yeah.
Thank you, Fatai.
So
it's a pleasure. Thank you very much for having me.
Adrian, go ahead.
Yeah, so you're obviously an advanced user of this stuff. So how long does it take you to do a study from start to scratch? So first of all, you've got to get the training data together, and then you've obviously got to do the study. So is it typically, it's about 3 to 4 weeks? How long does it take you now?
Are you talking about me to build that solution, or for my proponent to use the product I give him or her?
Well, so suddenly we got a demand. We need to solve this problem, and they ring you up and say, "Look, come here. We need some AI." And you don't know the wells, you don't know the field, you don't know the formation, you don't know what the issue is. You first of all have got to find the training data, and then you've got to come up with a solution through all these trials. You've got to figure out what the uncertainties are. So typically this takes 4 weeks. So how long does it take you now?
Again, it depends on the volume of data. It depends on the scope of the investigation. I mean, how many wells are we trying to bring in? How many fields are we involving? So basically, I would say that it will take like 1 week, I would say, based on the tool that I talked about AI Lab. It will take like 1 week, but the bulk of the time will be spent on the interpretation.
Yeah. So how long does that take?
Well, now it depends on the experts. It depends on how much time they devoted to. I mean, that is entirely out of the machine learning domain. The machine learning work ends at the point of prediction. Then it goes to the table of the experts to interpret, to make sense of what has been predicted. As you rightly said, sometimes there are explanations to certain results that the machine learning algorithms predict. So this has to be figured out by the experts by going back to the input data to see, like, for example, why are we having this prediction at this point? Why not here? Then we go back and say, okay, in the training data, we have a certain condition that triggers this in the output. So, I mean, that kind of feedback loop, I will call it. So it is not all about garbage in, garbage out. We're trying to make sense of the models we are building and the outputs we are getting from the models.
Are you convinced, Adrian, or are you going to stick to the other method?
No, I've never been convinced by AI, I have to say. So there's some pretty good examples I've seen now. Actually, you're predicting earthquakes, and basically you've got poor precision and basically poor accuracy in the data. There seems to be the area where it seems to be the best. So it's very much on the peripheral, but obviously production operations, like you were saying, for drilling near the bit and stuff like that, that's great. And forward predictions, because basically the other techniques break down. So when you've got nothing, AI is obviously the only solution, but typically we're dealing with small data. So Aramco is a very strange company, because when I was there, everything was in millions. When in the North Sea, everything was in thousands. So we were trying to add about 1,000 barrels a day to a well in the North Sea. We're adding 1 million barrels in Saudi Aramco. And the discoveries were billions, like 3 billion we found a discovery for. And yet in the North Sea, we were happy with 15 million. So Aramco is a unique beast. So I can see that you have to try AI in Aramco. And you're obviously doing good stuff.
Yeah, we try AI, but we try to do it very carefully.
We're kind of just about on time, though. We can really take any more time if we want to. Is there anyone want to ask or make any comments?
Yes.
Yeah, go ahead, Anton.
Yeah. Hello. thank you for the presentation, Dr. Fatai. So I have a more general question. Yeah. So what would you say are the general pitfalls associated in implementing AI or using machine learning algorithms? One I can totally relate it to is the assumption that when you have to write codes or use ML, then you should have better results, right? Because I think I've tried this for my PhD and just trying out to see just using basic correlation methods and also using machine learning algorithms and seeing that sometimes the ML algorithms are not better. So I just want to ask, what are other general pitfalls to avoid if someone is considering using machine learning to explore data or just make sense out of data?
Oh, okay, that's a very good question. And I think I mentioned this briefly during my talk. I think the very first pitfall that I will like to emphasize here is the people thinking that AI is a magic wand. That's the number one pitfall. I mean, AI is not magic. It is not, I mean, it must not solve all problems. So it is just an alternative method. So if it works, that's fine. If it doesn't, then please. However, there are two things to machine learning modeling. There is the data, there is the algorithm. So the two of them have to be optimized. If you have bad data, I mean, there is nothing you can do with bad data. You cannot get good out of bad. So the result of the model will be bad. So, and also if you have good data and you have a bad model, okay, if you don't optimize your model very well, if it either underfits or it overfits, then you won't get any good results. So you have to get good data and good model. So the two of them have to match. Now, for the data, we don't have any control. Well, we do have some control, right? At least we can QC. We can look for some, what do you call it? Some outliers. For example, I was working on a drilling data and I saw an ROP of, what was it? Of 3,000. I mean, this is not reasonable, right? I mean, you cannot, there is no way you can drill 3,000 feet in 1 hour. Is that possible? So I think the maximum I got from an expert is like 300, 400. I mean, even that is still on the high side. So if you are, so we have some control over the data that we use. So if we take all the due diligence by QC the data, remove the outliers or address the outliers, if not, because some people don't like to remove. Address the outliers. Some models don't like missing data, so remove them. Some models are able to handle missing data. Some models will fill it for you. So how good is that feeling? How reasonable are the some experts? I've worked with experts a lot, so I know what they like. I know what some of them don't like. Some of them don't like filling up missing data because they tell you, I mean, where do you get those values from? So they would definitely introduce some uncertainty into your model. So some prefer that, okay, if data is missing, remove the entire field. Don't fill anything. So when data is missing, it means it doesn't exist. So don't try to create any artificial values because it may impact your model. But sometimes if we remove missing data, then we are left with nothing or with too few. So we may have to live with it. So it depends. Now, that is all about data, okay? We have some control over data. So as long as we have done that, then the focus is on the model. I think the best way to build a machine learning model is to use automated hyperparameter tuning, okay? In that case, you don't have to do trial and error. I hate that nowadays. I mean, that's where I started from, but nowadays I stopped that. So I let some algorithms like Bayesian optimization, try different combinations of the tuning parameters for me. And then it also gives me the best point that doesn't, that fits in the goal of machine learning, which means avoiding underfitting, avoiding overfitting. So it gives me just the optimal model to solve my problem and then give me the prediction. So that way I know that, okay, this is the best the model can offer me. So it's the best based on the data.
Can I understand that, Fatai? Are you saying that you've got a model, like a governor model, which will then say, there's some data, let's try a random forest, let's try artificial neural network, and we the master knows enough to know which are likely to be the best ones. Is that what you're just saying? It for you, or are you not saying that?
That is part of it, but that was not what I really intended.
Okay, right.
What I intended is that for a particular algorithm, okay, instead of trying to tune different parameters, I increase the number of hidden neurons. I try to see the effect of that. Then I try some learning algorithms. I try, trying things by trial and error. I mean, for a particular algorithm. Okay, so it's better to actually optimize that process without that intensive human intervention. So let the machine figure things out, and then because the machine will do it faster and in a more consistent manner. So you get this out. Then it also comes to what you just mentioned now, and I have that in the tool I just mentioned. Instead of a user trying like neural networks, okay, see the results, and then try SVM, see the result, try something else. You can actually try them, but if you are running the program on a supercomputer, you can actually try all of them in parallel or try them sequentially. So you have all the results. Then you can use the human judgment to say, okay, among all these models, this is the best. Then I will go with this.
Fantastic, very interesting. Are there any other remarks or comments that people want to just pitch in to Fatai before we finish with? Anyone else want to say anything?
There was a question in the chat about how would you recommend learning, how to get started learning machine learning.
Oh, okay. That's very interesting from Emmanuel Olaoluwa. You start by, actually, my mantra is that you start learning by doing. So if you learn if you take all the courses in Coursera, okay, and without doing anything, you wouldn't go anywhere. So even if you take only one course, just to understand the fundamentals, then try to lay your hand on some problems, even if it is some already solved problem, just to put yourself in the line. So yeah, learn by doing. So have enough fundamental, but continue to learn by doing. So that is what I will recommend very briefly, because the more you do, the more you know. I mean, I started from a very low or shallow level, but now I'm not an expert, but I know that I'm no more where I was. I mean, where I started from. So by doing, when you do, you face challenges, and then you rise over them, and then you become an expert in doing that. So I mean, it doesn't come easily. So you have to take some time. You have to make mistakes. You have to fail a number of times, and then overcoming those failures and obstacles makes you a better person. So
I got one last question.
Yeah, go for it.
So on the example you said with deep learning, you said the more data you have, deep learning gives you a better performance. That was on your summary slide. So what do you actually mean by performance then? Is that performance is just how quickly you process the data, or is it actually the fitness of the sort of the truth and the new data you've created, the new knowledge? So what is performance?
Okay, thank you very much. That's another very good question. The performance will be determined by the user. So what exactly is the goal of a study? So if the goal is to, let's say, predict permeability, for example, or predict porosity, okay, what is the goal? I mean, how do you determine when you have a good model? I think you look at many things. I mean, one bad practice, which I wouldn't recommend anyone to do, is to take only one criterion and use that to judge your model. No, that is not a good practice. Use different criteria so that when you combine all of them, then you get a robust assessment. Don't use only R-square, because R-square only gives you the trend, okay? It's your prediction following the same trend as the actual. That's what it gives you. You get no idea of the error. I mean, how close you are. That gives you, I mean, you get no idea of that. So if you have R-square, you say, okay, I have my prediction has the same trend as my target. Okay, fine, that's good. But how am I doing? How close am I? How close is my prediction to the target? I mean, that's another good thing. And again, the other way around, if you focus on only how close and there is no trend, that's another bad thing. So I think we have to combine a number of criteria to actually arrive at a very robust measure of performance. The minimum I would recommend is have R-square with any of the error measures. So that as you are looking at the trend, then you're also looking at your closeness to the target. So that's the minimum. And there are various measures out there that you can use.
I'm conscious we're kind of quarter to 7. So I think, Fatai, that's truly amazing. Thank you very much indeed for a very articulate, very interesting and fluent presentation on a very difficult subject. But you've done us very well. I'm really pleased. Thank you very much.
Thank you so much for having me.
Yeah, well, even Adrian.
Thank you very much. Thank you very much.
Get a clap from Adrian. You've got to be doing.
And hope to meet you soon.
So likewise. So we've been sitting down for about an hour and a bit. So can I suggest that we take 10 minutes or so, and then Deepak can start after that. So let's come back for 7 o'clock. So just a bit more than that, 15 minutes time, and then Deepak will start and talk to us. Okay. So see you all in about 15 minutes. Bye bye.